Okay, so yeah, in this presentation, I'd just like to explain some of the work, the simulators that we've been developing in the areas of floods, earthquakes and bushfires using a multi-agent system approach. Oops. So I'd like to give a flavour of our work and to see the power that an agent-based approach allows us to answer some questions on crisis management. And we've seen that previously with Odil's excellent presentation, and yesterday with Marc Roulet's presentation on multi-agent simulation of floods in Paris. But first of all, I want to go into a little bit of detail about what agent-based simulation is. Okay, so a software agent, we can basically think of it as just a piece of code. So something like an object in object-oriented programming. So a software agent has a set of characteristics, so attributes. It has a set of actions or things that it can do, behaviors. It can communicate with other agents, so typically by sending messages, and when an agent receives a message, then that can invoke an action in that agent. So agents can also receive information from their environment, and that may cause an action as well. But the main thing is that agents are autonomous in the sense that when they get these messages, it's the agent that decides whether to act or not. So agents can have different levels of intelligence. So they can be just purely reactive agents, which can be modeled by simple what if rules, if then rules. Or they can be more proactive, they can have long-term plans and goals that they want to achieve. So we can put different levels of intelligence into our agents. So typically in the work that we've been doing, for us, agents represent people. So they may be civilians, they may be firefighters, they may be decision makers or police, etc. And the thing is, once you put these agents together, you have this multi-agent system. So the idea is that even if the agents are programmed with very simple behaviors, then the overall resulting behavior of the community of agents can be very complex. So it's very much a bottom-up approach where we're modeling the individual behaviors of people and their individual attributes, putting them together and see what happens at a higher level. So at this higher macro level, we're interested in observing emergent phenomena. So for example, the emergence of cooperation in a group of people. At the lower level, we're interested in looking at the individual behaviors of the individual agents. So what we're doing is we're creating this artificial world. So we have our agents here, our animate agents. We can organize those agents into, say, communities. So we can organize them into family groups, for example. We also have inanimate agents, so they may be things like buildings. Our agents, as I've said previously, have attributes and actions that they can do. And in looking at the simulator, we're observing what goes on in this situation, and obviously it's creating data. So how we build these models. So first of all, typically we look at the real situation, and from that we build a model which is, of course, an abstract representation of that real situation. The model is then programmed and driven with input parameters. And then once it's calibrated and validated, then we can start doing experiments. And hopefully those experiments, those what if kind of questions that we ask, will tell us something about the real situation. So, as I said at the beginning, we've been developing quite a few simulators, and here are some of the questions that we've been looking at. And the first one is how to help stakeholders explore the options in managing risk in coastal flooding. And for this, I'm going to pass over to Elise, who's going to explain the VITO simulator. So Elise, do you want me to stop sharing my screen and you share yours? Or do you just...
No, it's okay. You can go on, and I just invite you to move to the next slide. Thank you. Okay. So next, thank you. So to address this first operational question, we with a group of researchers from different research centers, we developed a platform in the context of Xynthia winter storm. This storm revealed a lack of culture, of risk culture among the population, and especially among policymakers. And moreover, we observed that concrete dikes are the most preventive strategy adopted on a fresh coastline. So for this reason, we decided to build up a participatory platform, which was based on an agent-based simulator, and which is called LITOSIM, in order to raise awareness among local stakeholders. So what is LITOSIM? It's a participatory simulation based on a coastal flooding modeling, on land planning modeling, and also a role-playing game. So during 3-hour workshops, the different participants, who are organized in 4 teams, have to manage a municipal territory on a digital model with the help of digital tablets. Next, please. So they have these digital tablets, and on the tablets, you can see a display on the tablets of the left-hand side of the slide. They can either change land use or manage the coastlines, defenses, and like sand dunes or dikes, and they have administrative and financial constraints. Sometimes a coastal flooding occurs, and the physical simulation of flooding is launched. So this physical modeling, which was calibrated with real event data, takes into account the actions that were carried out by the different players. So we use the Gamma platform to set up this ABM. Next, please. During this display, the players visualize the simulated flooding, and they can react, discuss about the effects of their strategy they carried out. And they are also encouraged to develop cooperation strategies between the different municipalities. Next. At the end of the workshop, a general debriefing is organized so that the different participants can analyze their experience of the workshop in light also of their experience in real world life. Next, please. So the main results that we obtained from these different workshops that were carried out in different territories, and especially in the island of Oléron, which is the first territory where the LITOSIM platform was applied. We observed that the players changed strategy after flooding events, which are represented by red lines on the graphic of the left-hand side figure. And we observe also that these different participants improved their knowledge of soft measures like the role of adapting housing, of the buffer role of wetlands, etc. And they also changed their mind on the relocation, though we observe a low acceptability. And finally, the different participants highlighted the fact that the inter-municipal scale was adapted to develop an integrated risk prevention strategy. Thank you.
Okay, so thanks Elise for that. So the next point that I want to address is some work that Carol's been doing, C.Adam. Unfortunately, Carol can't be here today, so I'm just going to present a quick slide about her work on how to raise public awareness to floods and how she's done that through two simulators, one called VigiFlood and another called Sprite. So VigiFlood is a serious game that is used to raise awareness about risk communication, and in particular the impact that false alarms have on the population. So in this game, the user, which is basically a civilian, changes perspective by taking the role of an emergency communicator who has to set the level of vigilance to alert the population. So what I would invite you to do here is sometimes you may want to play with this simulator, which is online here, and also take a look at Carol's site here. The second simulator that she's been working on is a participative simulator. And here the idea is to help decision makers understand the consequences of their decisions concerning the flooding on Orléans Island. Sorry. An interesting thing about this is that it's used by students at the University of Bordeaux to train them in natural risk management. So here the students have to play the role of a local councillor, and they're trying to ensure the safety and well-being of the residents, but at the same time they need to balance this with maximising performance with respect to economics, how much budget they have, environmental issues, etc. And again, there's more information on this on Carol's site here. Okay, so I'm just going to move over now and talk a little bit about social attachment and how social attachment affects evacuation. And this is a model that was developed by Julius Spangate, who's actually with us today. He's a former PhD student of mine, and it was a collaboration between LIG and PACTE. So the problem is that the simulators on evacuation that we develop rarely take into account real behaviours. They tend to assume that people will behave in an ideal way, but actually we know from previous reports, from videos, etc., that people don't do that. People are attached, they have a social attachment to their family, to belongings, etc. So one of the questions that we looked at in Julius's thesis was, how does this social attachment affect evacuation? And for this, we used Mawson's social attachment theory. So a person can, have a social attachment to another person, a husband or wife, or a group of people, so a family, a place, typically a home, the tasks that they may be doing, family pets, or objects. So during an evacuation, people will maybe try and find their family. They may gather their belongings together, their MacBook, their phones, etc. And this obviously affects the time for evacuation. So we developed a simulator which was simulating what would happen in the case of an earthquake in Grenoble. Now, Grenoble won't have a very large earthquake, but it is in an average earthquake danger zone. So if there is an earthquake, there can be quite a bit of damage caused by the falling debris, even though it may not be a very strong earthquake. So into this simulator, we were inputting geospatial data, data on vulnerability of buildings, demographic data. We also used a lot of reports from the literature on social behaviours, and we also used video observations to help us determine how people behave. Now, this work has been extended by Ruba Iskandar as well, who will say a little bit more in the next presentation about the details that she's gone into in this. So in terms of the simulator, I'm going to have to explain this a little bit, but we can set the parameters here on the left. These roads, these pink areas here are the roads, and we can see little black dots, which are actually the agents. So those are people who were moving around after this earthquake. The cone that you can see around them is their area of visibility, which changes due to various factors. The buildings are shown here in yellow and red. The red buildings indicate those buildings which are very vulnerable to collapse. And my computer has frozen. Can you still hear me? Yeah. I've got a little bit of a problem because my computer is frozen. My keyboard is frozen. So
Want me to share the slides?
Yeah. Yeah, everything is frozen here, so I can't stop
Maybe you stop and re-begin.
I can share the screen if Julie can still.
Yeah.
Okay. I'm just.
Okay. So maybe can you stop the sharing?
I stop it. Yes. It doesn't want to stop, I think.
Elise, maybe you can try, and it will stop the screen of Julie.
Okay, Julie, you've frozen everything. So
it's okay. Can you see my screen?
No.
I'm supposed to be sharing.
Oh, it's okay.
Yeah,
right.
It's okay. Okay.
All right.
So,
yeah. Thank you.
Julie, I just moved to your slide. Can you still hear us?
Okay.
Julie?
Maybe Julie will not see that. Reboot the computer, that's it?
Okay, maybe I move on. I may not have the perfect transition, I'm sorry. I mean, you're not saying what she wanted to say exactly, but I try to well, I try to move on. Okay, so in order to validate the model, that we took into account several components, we asked several people to come and see the model and talk about the model from different domains. So from experts, scientific experts, from social scientists, from geoscientists. We also validated with the statisticians and computer scientists. And we also invited several practitioners. Julie? No, she's still off. Okay. We also asked several practitioners from the firemen session of Isère, the Grenoble Mayor's office, and the Parne to talk about the model that was being developed by Julius. And we together validated the conceptual model. So several scenarios were tested, and in order to identify the impact of several parameters, like the intensity of the earthquake, the fact that we had a day or night scenario, and we tried to track several we tracked several parameters to observe the results of the simulation, like the number of dead people, the number of injured people, the time that was needed for the people to arrive to the safe areas, and the fact that there were casualties on the route, on their route. So different results emerged from this study. First, the important role of social interactions and social dynamics in the efficiency of the evacuation, and especially the social attachment role played an important role to the arrival in safe places, especially at night. Of course, we observed that as the intensity increases, there were fewer number of people arriving in safe areas. I'm a bit...
Okay, I'm
Thank you.
Sorry, so if I can share my screen, I can take over. Sorry about that. I think I'm just going to keep my video off for the last few slides because...
Do you want to share your screen or do I share mine?
Yeah, if I can share my screen now.
Okay.
Oops. Okay.
Welcome back, Julie.
Thank you. Thank you. Sorry.
Good to see you.
Okay, so yeah, sorry, I'll just keep my video off for the last few slides. So the last one that I want to talk about is how communication between stakeholders affects evacuation. And this is a bushfire model. So this is some work that was done between LIG and IRED. And the context of this is the increased prevalence of bushfires in Australia. And in particular, the Black Saturday bushfire in 2009, which killed 173 people. So what we're trying to do here is simulate the behaviour of the population in a part of the state of Victoria during a bushfire. And work on this actually began in 2017. And one of the interesting things about it is that we've been able to combine several different approaches. So agent-based simulation, we adapted an agent communication language. We looked at cognitive modeling, and in particular something called the belief, desire, intention architecture. And we also incorporated a GIS. So I'm not going to explain all of this because it's quite complicated. But in terms of the communication, we have the different agents here, so civilians, firefighters, police, etc. And then they can communicate with each other using an adaptation of what's called FIPA's ACL. So it's an agent communication language. So for example, an authority can ask the police to go to a certain location, or a civilian can ask the police where the location of a shelter is or where the fire is, etc. We also implemented the idea of goals, plans and actions. And here is just a small snapshot of some goals. So for example, we have the goal of stopping the fire, which can be broken down into sub-goals. And for those goals, we can develop plans to achieve those goals. And then those plans are made up of specific actions for each of the agents. So we have the simulator here. We've got the ability with the simulator to be able to zoom in or to zoom out and see different scales. We can see the buildings here, and when we zoom in, we can see the agents moving around on these roads, and also the firefighters going to tackle certain to tackle the fires. So we can track the communications between civilians, helicopters, firefighters, etc. And this allows us to test different communication strategies. We can also track civilians' health, so whether people are okay, the number of dead, the number of injured, etc. And we can also track the evolution of the fire, so the direction that the fire is moving in, the current fires that are there, the extinguished fires. We can track the location and the movement of the actors. And this work is actually continuing with CSIRO, which is the Australian equivalent, I guess, of CNRS. So we've been working with them on this. And at the bottom of this screen, there's some more information that's related to this work.
Excuse me, Julie, you have to conclude quickly.
Yes, and just in time, here's a slide.
Perfect.
So what we've seen is that we can apply agent-based modelling to different types of hazards. It allows us to take into account not only the physical dimension, but also the social dimension of disaster situations. However, it does require quite a strong multidisciplinary approach. And we can see that if we have agent-based simulators combined with serious games, this can allow us to address a variety of operational questions. So we can use ABM if real data is available to represent real situations, but we can also use it for abstract situations as well. So ABM is very powerful, but we also have some problems that we have to address. So firstly, how do we obtain the data for the models? How can these models scale? What level of detail do we need to go into in our models? We've got an important issue about validation, because if our models are not validated, then we really can't trust the results. We also have issues or choices to make about what kinds of agents to use. And lastly, is it possible to reuse elements of our simulators because we're developing different simulators for different contexts, different situations. So can we reuse some of those components? Okay, so sorry about that delay.